Okay, off we go. So last time we were talking about different kinds of line integrals. We were talking about scalar line integrals, but then also vector line integrals. Very, very different construction. They're both integrals that are computed over curves, so they seem similar, and they are kind of similar, right? But they're also different in significant ways, and thus the distinction. Okay, so we've said a bunch of things about line integrals. Next one, we have symmetry theorems. So these are, it's just a wonderful theorem. Just like with double integrals, just like with triple integrals. And you'll notice that the way I've written the theorem, I have deliberately laid it out on the page to look exactly like the symmetry theorem for double integrals and the symmetry theorem for triple integrals. That's because it's morally equivalent, right? And again, same warnings. Both conditions have to hold. And again, you have to use the same line, right? So the same little asterisk, same little costs, right? Same risks, of course, as well. But that said, powerful theorem, very useful, a lot of circumstances. Okay, now here's the warning. This is unexpected, perhaps. A lot of students get stung on this, right? And there is no version of the following danger with double integrals or triple integrals. And that is, it only works for scalar line integrals, not for vector line integrals. It just doesn't work for vector line integrals. Right? So be very, very careful. If you want to apply the odd symmetry theorem to a line integral, make sure it is a scalar line integral. It's got to be a scalar line integral. Let me try to show you why for a vector line integral it just doesn't work. Here's a vector line integral, and when I say an odd symmetry theorem, what I mean is odd being characteristic of the integrand, namely the vector field. Okay. So here's the thing. Let's look at this instead in the form of this. Now, this is just an alternative way to write a vector line integral, right? And so now we imagine our scenario where we've got some domain, some curve, and I'm drawing that's my attempt to draw a nice symmetric curve, symmetric over that line, and I chop it up into a bunch of little pieces as usual, and you could imagine this little piece right there of size ds and this little piece right there of size ds, right? Same ds, exactly the same, just as it's supposed to be. But then here's where it all goes wrong, and that is, keep in mind, we've also got this t here. And that t, if you look at the unit tangent vector on the left piece, and then you look at the unit tangent vector on the right piece that's supposed to be its buddy, it's supposed to be sort of all the same except for a single minus sign, and nope. Right? This is not the same. Right? So this dx vector altogether, dx, this product is just not the same on both sides. And so oddness of the vector field just doesn't cut it. And here's what's worse. This t, not only are they not the same on sort of, opposing pieces, they're also not negatives of each other. So, it's just a mess. Now that said, there is a relationship between them. There is a clever way that you can sort of adapt to the circumstance and create a different kind of symmetry theorem. That's true. But that different kind of symmetry theorem is more trouble than it's worth, I think. Right? What I would advise is if you're looking at a vector line integral for one thing, do not try to cite any sort of an odd symmetry theorem for vector line integrals. Again, merely having oddness of your vector field, you got nothing. It just doesn't work. What you can do, though, is take your vector line integral, rewrite it like this. Once you have it in this form, realize that, let's see here, do it like this. This integrand, not f, but f dot t, is the integrand for what is, in fact, now a scalar line integral. And there you can cite the symmetry theorem for the scalar line integral that we already talked about. Okay, so that's what you have to be careful with. Okay, moving along, we're done with section 6.1 now, on to 6.2. Green's theorem is going to be our first example of a collection of theorems that are kind of jaw-dropping, kind of unexpected in how they come up. They're really weird. And they all kind of have some of the same earmarks in certain ways, even though they apply in very different circumstances. So you're going to notice all this. Of course, you're going to hear me pounding on it endlessly, right, as well. But anyway, the point being, this is the first in a line of very closely connected theorems. And so I'm going to present all of these theorems in what I'm going to call as closely analogous ways as possible. I think this is helpful for seeing the connections and comparisons between them. And there are subtleties to how to look at these. So I'm going to make some odd-seeming statements, the purpose of which is to help you understand subtle ideas that are underlying all of these theorems. Okay, so here we go. Very first thing we're going to talk about is the idea of boundary as being an oriented thing. Now, we've never done such a thing before, right? Every time we've said the word boundary, it's this simple idea of, well, it's the edge. It's where our set stops and not set begins, right? It's just a real simple idea. Boundary, henceforth, for the rest of this class, boundary is an oriented thing. And if it's going to be oriented, it has to be oriented in a specific way. And if it's going to be specific, we have to be able to say precisely what is this specific orientation. And here's the rule. If you have a region, some two-dimensional region, by the way, this is going to be strictly in R2. This convention I'm about to describe is strictly in R2. Green's theorem that we're in the process of developing is strictly in R2. Starting in R2, there is a three-dimensional kind of sort of version in a way, arguably a couple of kind of analogous versions. This theorem strictly in R2. If you have a region in R2, and you talk about its boundary curve. So now I've just drawn part of the boundary here. We have part of this region D in green. Here's part of its boundary curve there in purple. The orientation, the direction that you should be going, the direction that is the correct, the positive, if you will, direction along that boundary curve is the one that makes, I wanted this to be in a different color, sorry, red. The one that makes the region be on your left. Ooh, that doesn't show up well, does it? Okay, let me make a different color choice here. How about yellow? That doesn't really okay, bad color options there. I wonder if I go really hard. No. Anyway, here, I'll do it like this. There we go. Okay, so we got two different directions that we could move along this purple curve. I could go this way. I could go this way. It's like, think of it like a road. You can drive two different directions along a road. Always go along that boundary such that as you go that way, the region's on your left. Does that make sense? Okay. All right. Okay. Now notice, while that has me going this direction on what you might call the underside there, notice then if everything is sort of turned around, if I have a region like this, and if I'm looking at the portion of the boundary along the top, right, then notice I have to go this way in order to have the region on my left. Right? So try not to oversimplify. Always go to the left or always go to the right. It's not that simple. Go whichever way puts the region whose boundary you're talking about on your left. Now here's another mistake that students will very often make, and that is to look at this picture here and say, oh, okay, it always goes counterclockwise. right? Because, I mean, if you look at this kind of lumpy thing here, well, you do counterclockwise is the way you would go to have the region on your left. Not that simple. It's not always counterclockwise because easy counterexample, look over here. If I have a solid that has holes in it, like this, which direction do I go, let's say from this point, to have the region on my left? Well, I have to go that way, which of course would make it clockwise. Okay, so careful. Right? Now, that said, it does remain that most of the time the regions that we're talking about are what we call simply connected. In other words, they don't have any holes in them. Yeah, okay, that's true most of the time, right? And in such cases, yes, it is true that it goes counterclockwise. If you want to remember that as a convenience, that's fine. Just remember that's the slightly sloppy, not always true shortcut, and in general, you have to be careful. Okay. All right, next, let's talk about this thing called accumulation. Now, we've talked about accumulation a lot, right? I mean, we've defined various different kinds of integrals, in all of which we have this idea of accumulation, that the whole is the sum of the parts. That when you chop your domain up into little pieces, you can compute the quantity in question on each little piece, and then when you add up over all the pieces, you get the answer to the question you're looking for the whole. So the whole is the sum of the parts, chop it up, add it up, however you want to say it. Nice, succinct term, accumulation, accumulating quantities, etc. Okay, all integrals are about accumulating quantities. Okay, so right, so if we look, for example, at this region here, right, and if I were to chop that up and say, well, there's this sort of green part over there, and then there's this kind of blue part over there, we want the orange to equal to the green plus the blue. Now, if we were talking about mass, definitely works, right? The mass in the orange region is clearly the mass in the green plus the mass in the blue. That's the way mass works. Right? If we're talking about population, again, of course, right? These are accumulating quantities. Now, I want to emphasize, though, perimeter does not accumulate over areas. And now, just to be clear, when I say accumulating over something, what I mean is looking at a situation kind of like this. It's the area that I'm chopping up into little pieces. I'm not chopping up the boundary into little pieces. That's not what we're talking about. I'm talking about if you have an area, if you chop up the area into pieces, is the whole the sum of the parts? And I claim perimeter fails. Right? The perimeter of the green region plus the perimeter of the blue region is not the perimeter of the orange region. Right? Everybody happy? Okay. So accumulation's awesome. We love it when stuff accumulates because when something accumulates, you can do it with integrals, which we know how to do, and that's very powerful, right? But you have to be on the lookout for things that are not actually accumulating quantities. And if you try to compute the perimeter of this thing by chopping it up into little pieces, wildly, wildly wrong answers. Okay. All right, so here's the surprising thing. Really surprising. Let's see here. I'll use purple. Boundary circulation is an accumulating quantity. Now let me remind you what boundary circulation is. Here we go. Okay. Boundary circulation is line integral. Specifically, line integral over a closed curve. And if you think about it, if you have a boundary, that boundary is closed. Okay. So I'm gonna say boundary circulation just to emphasize that it's very important that we think of it as being something that happens on the boundary, at least in some sense. But technically, of course, the word circulation, right, already means closed curve. Okay, so anyway, boundary circulation, the big idea is that we're measuring the extent to which the vector field is kind of flowing along this closed curve, and the closed curve has to kind of go around. It has to go all the way around, and so circulation is measuring the extent to which, in some sense, the fluid kind of is going around. That's the term circulation. We talked about this previously. You might even take the view that circulation is kind of, in a sense, measuring how the fluid is rotating-ish, kind of, sort of, in a way. Right? Or certainly, if there were something floating in this fluid, how would that floating thing be rotating? Okay. All right, so that's what circulation is, just as a reminder again. And again, I claim that it accumulates. It's really counterintuitive, in fact, because if you take a casual, sloppy take on this, then, well, here's where I would compute the circulation around the whole boundary, and here's where I would compute the circulation around the left piece, and here's where I would compute the circulation around the right piece. And you feel like there's a lot that tracks, right? I mean, the purple and the green are tracking there, and then the purple and the blue are tracking there. But what's up with all this stuff in the middle? Now, there's green and blue in there, but there's no purple in there. So how could the whole be the sum of the parts if there's clearly the parts are doing stuff that's not in the whole? Right? It doesn't seem like it ought to work. But let's be more careful about it now. And keep in mind, when you're talking about circulations, you're talking about a vector line integral. It doesn't happen on a curve. It happens on an oriented curve. The orientation is critical. And here is the boundary of D1 understood with its orientation. Right? And again, keep in mind the word boundary. Whenever you see the word boundary, right, moving such that the region's on your left, or, most of the time counterclockwise, as I have it drawn here. Likewise, the boundary circulation on the right, like that. The boundary of the whole, right, is going to be kind of sort of like this. This is the picture we really have to be looking at. The orientations matter. And then when I observe that, hey, cool, guess what? It's kind of tracking along in there, right? The purple and the green are the exact same thing, same direction and everything. So these really do kind of cancel each other out. And then likewise over here, these really do kind of cancel each other out. And then now to what's left, the stuff that's in the parts that's not in the whole. What you see now, very importantly, these have opposite orientations. They are non-zero. They're line integrals over a little piece of curve, each one of them, but it's the exact same piece of curve with exact opposite orientations, and they cancel too. And so what you're left with is no difference, right? So the whole truly is the sum of the parts. Counterintuitive, again, you got to be careful with the orientations to see how this actually plays out. It doesn't seem like it should, but it does. So very counterintuitive fact. Boundary circulation is an accumulating quantity. Ultimately, deep down, this is what makes Green's theorem work that we're in the process of developing. This is the main point. Okay, now I'm going to point out you can chop it up to as many little pieces as you want. It doesn't matter. I mean, I started off with chopping into 2 pieces because, easy, right? But let's suppose we're looking at something like this. And again, I've got the boundary of the whole kind of cruising along like that. And then I've got these little pieces. So, okay, well, there's this. Here's the boundary of this little rectangle. Right, and here's the boundary of this little rectangle over here. And when you start adding up these boundaries, or these boundary circulations on the interior, notice that again, these sort of internal pieces, they always pair up. You're always going exact opposite directions on these little pieces, and they cancel. Right? Yes?
What is similar, like, theory of life for kind of like nested circulations that are just all inside each other?
I'm not sure what you mean by
it. Like a box and then a box inside goes for infinite. Does that make sense?
I'm sorry, I don't quite understand. It sounds like you're describing a new construction. Is that right?
Yeah, like if we have like one of those boxes on that graph.
Yeah.
And then we had a box inside of that going the other way. And
Oh.
a box inside that going the other way. Is that like a similar theory or like application?
I mean, I will say it doesn't matter how you chop up the area. You can chop up the area any way you want. And because it doesn't really matter that these are rectangles, right? All that matters is that there's this edge, and being in the interior, it's part of the boundary of what's on the left side of it, and it's also part of the boundary of what's on the right side of it. And those two, they're always opposite sides, and they're always going to be oriented oppositely if you follow the counterclockwise rule. So yeah, it doesn't matter how you slice it up. I'm not sure if that answered your question. Did that?
I think it
Okay. Yeah. So it's mysterious how well this works. Is everybody okay? All right. Okay. So now some pieces don't cancel. Now again, we get cancellation there and there and there and there, etc., here and here. But wait a second, not here. That little piece right there, it's part of the boundary of this, but there is no something on the other side for it to cancel with. So that piece remains. Right? Likewise, this piece remains, and this piece, and that piece. And, well, if you notice, in fact, every piece, that's part of the boundary of the whole. And so, again, slice it up all you want. Doesn't matter. All the internal pieces are going to cancel, and the whole is the sum of the parts. Okay. Wonderful little fact. Okay, now there is a particular point of view that you can take that ends up being really, really valuable, and this is going to seem unnatural at first. You'll eventually realize it's actually extremely natural, and it's going to take me a while to kind of develop up to why I claim it's so natural. But the big idea I want to try to persuade you of is that if you wanted to, not that you have to, but if you wanted to, and I claim that we do want to, again, that's going to come down the road. If you wanted to, you could think of boundary circulation, even though it's actually computed on the boundary. It says so right in the name, right? Even though it's computed on the boundary, you can think of this as a kind of a stuff that's distributed over the interior, which seems super weird. Why in the world would anyone ever do that? Right? Yeah?
You're adding scalars here.
I'm sorry?
You're adding scalar values.
Yes.
But how does... I thought the point was we're cancelling vectors.
The direction vectors are why these scalar quantities cancel, right? So in other words, if I want to look at, let me just come back up to where we had been. If I want to look at the integral on this piece, that's part of this, right? And the integral on this piece, and that's part of this. I mean, you're right that these directions hidden inside of the dx vectors, those directions are vectors, right? But the quantities themselves, this line integral, vector line integral, its resulting value is a scalar, but there's vectors inside of it that are why the directions cancel, and thus, yeah.
So if you have those two regions, and you calculate the boundary circulation, put them together, let's say the left one's 2 and the right one's 3. You get 5.
Yep.
If you separate them,
yes,
you still get 5, but then
correct.
You've got more boundary.
I'm not understanding the point.
If you have those two regions, one's 2, one's 3.
Yes.
And you calculate the boundary, you get 5. But
correct.
Let's say
Wait, hang on. Let me just document what you're saying. You're saying that this line integral is 2.
Yeah.
So we have a big 2 right here, right? And then now you're saying this line integral is 3.
Yeah.
Cool, fine. Okay, now go ahead.
And you take the whole boundary.
Oh, yeah. Okay, so then the boundary of the hole, so around this hole,
That would be 5.
it is indeed 5. Now, what do
Let's
you...
say you create a gap between...
now you're changing the set.
Oh.
Right, I'm specifically making a statement about this set where this specific lump. Right, now if you want to talk about a different set, then everything changes. I'm talking about this set.
Okay.
I mean, is that right? I mean, you see what I'm saying?
I'm slightly confused as to why let's say you do separate.
But see, think about any integral that we've ever studied back in when we were doing double integrals. If you change the domain, you have a totally different question. You're going to get a different answer.
Okay.
Does that make sense?
Yeah.
The particular, a lot of detail devils involved here, right? So specifically, I'm talking about a region a specific region. This is the one we're looking at, right?
Yeah.
And I'm going to cut it a specific way. Now, you could argue it doesn't matter how I cut it, but nevertheless, I do have to actually cut it, which means I'm going to cut in some actual specific way.
Okay.
Yeah. Okay. Yeah. Okay. How are we doing? Is everybody all right? Okay. So, let's look at the boundary circulation here. Now, I just made up a hypothetical scenario here that really doesn't matter, but the point is, I'm going to suppose that the total circulation here is 33, let's just say, right? Where is that 33? Well, you could say it's on the boundary if you want to. Right? Again, I'm going to make the case that we're going to have a preference for thinking of it in a different way. And so, for example, I know that if I look along this purple curve here, there's going to be a certain amount of circulation. Apparently, that circulation is 1, and then I can go all the way around and look at different pieces. Let's look at this piece right here, going like that. Let's say that circulation 6. Now, I know the whole is the sum of the parts. I know that these 9 individual boundary circulations add up to 33. So, reasonable point of view, where is this 33? Well, 6 of that 33 is inside of this box. Right? And let's see here, 7 of that 33 is inside of this box. So I can think of that circulation as literally being distributed over the interior. Now, just to give you a different way to visualize it, that seems a lot less controversial. I can draw this circulation, again, as being something that I associate to this area. Right? Keep in mind, it is the area that I divide into pieces. Now, how I compute my accumulating quantity on this area. Okay, that depends on the accumulating quantity, whatever. The point is it's an accumulating quantity. And if I were to make the statement that the accumulating quantity on this hole is the sum of that, I didn't want that, gosh, I want to be in pencil mode. The amount of the accumulating quantity on this purple piece plus the amount of accumulating quantity on this dark blue piece plus the amount of accumulating quantity on this light blue piece, etc., going all the way around. And of course, uncontroversial, the whole is the sum of the parts. That's what accumulation means. And if I were to then say that the amount of this accumulating quantity in here is, whatever the accumulating quantity is for that piece, of course. Right? So, it's not that we're computing boundary circulation in the interior, it's that it behaves algebraically, arithmetically. It behaves as if it's actually something that's in the interior. So, anyway, it's a weird choice, but it is it's going to end up being a valuable way to think about it. So boundary circulation, the punchline is, boundary circulation behaves like stuff. Right? If I talk about mass, forget about circulation. If I talk about mass, the amount of mass in this green region, where is the mass? Well, some of it's in there, some of it's in there. If you want to know how much is in each box, fine. Do the computation on that box. The mass has location. that you can detect by how you chop it up into pieces. Same with boundary circulation. So it's counterintuitive, but try to think of boundary circulation as being like a visceral stuff that you can touch and that, kind of like mass. Because algebraically, that won't lead you astray. Okay, what do we do with stuff? Well, we can talk about density. So, for example, if I have some area here, and if there's a certain amount of mass or population or any other accumulating quantity that we've ever talked about that you might imagine is being distributed over an area, right? Standard idea is to say, okay, well, there's a certain amount of mass within a certain amount of area. Let's talk about this idea of a density. And the density is, let's see here, color choices. The density is mass per unit area. Or if this were population per unit area. In general, then, accumulating quantity per unit area as a generalization. All right, well, there's various accumulating quantities, and one of them that I can talk about for a two-dimensional region, right, of some little piece of area, I can talk about the accumulating quantity called boundary circulation. So again, now you think of it as happening on the boundary, but we're not going to think of it that way anymore. We're going to think of that as something that is distributed over the interior, not because it is, but because it behaves as if it is. And it's going to be convenient for us to think of it this way. Okay, so in the same way that we can talk about mass density like that, we can talk about what we're going to call, and I hope this is no surprise, let's see here, I'm making a color choice here, I'll use dark green, I guess. Oh gosh, I wanted to be in highlighter mode. Sorry. Circulation density. Totally analogous to the idea of mass density. Accumulating quantity per unit size. It's just a different accumulating quantity. And in the same way that, again, if you're talking about population, that per unit area is population density. So it's just following along in the analogy. Accumulating quantity per unit size is density. All right, weird, isn't it? I freely admit this is a weird way to think about things. It turns out it's bonkers useful. As we're going to see in just a moment. All right, so with all of that noted, let me sort of get rid of that. Let's talk about how to compute circulation density, and this is where I'm going to sweep some stuff under the rug because we just kind of, we only have so much time in the class, and the details of how to go about computing this thing called circulation density, there's a certain amount of intricacy to it. It's not that bad. It's in the book. You can read it if you want. I just don't feel that those details are critical to what y'all are going to be doing with this stuff. So I'm just going to write down the formula. And here it is. It's dq dx minus dp dy. Nice, simple little formula. Given a vector field, of course, we're talking about circulation. Circulation's of a vector field, so if that vector field has components B and Q, this little formula computes your circulation density. This is the thing you can do integrals with to compute the total, just like population density, just like mass density. Now, the notations for this, there's a bunch of different creative ideas about what to call this. I like calling it Green's operator because this is a differential operator that is the critical element of Green's theorem. And so Green's operator seems pretty reasonable to me. I like to abbreviate that with GRN. That's convenient, right? A lot of people like to call this rote. Looks like rot, but wrote, because the idea is that what this is measuring to some extent is how the vector field has a rotational aspect to it. Keep in mind, circulation. What is circulation? Circulation is a way of measuring how much the vector field is kind of following around a boundary curve that makes a circle like the circle, right? So this is the quantity in question is about how the fluid rotates. So rot is a reasonable choice that I like. Along those same lines, some people like to call this curl. That's fine. Not my preference. There is another kind of curl. You may recall back in Chapter 3 we talked about curl. It was in 3 dimensions, wasn't it? This is in 2 dimensions. Curl that we talked about back in Chapter 3 was a vector. This is a scalar. So it turns out that, yeah, they are connected to each other, similar in certain ways, and there's strong analogies, but to me, I think it blurs the distinctions to call them both by the same name. So my own personal preference is sort of opposed to that choice right there. And then I really have a significant problem with this one. I'm going to go ahead and put this one in red. This one is I'm just aghast. They write del cross f dot k, and here's the thing: cross product really very much only works in 3 dimensions. What are you doing? Right? And then k, there is no k. That's a 3-dimensional thing. ij is all you have in 2 dimensions, right? So this is really using a lot of imagination. Now that said, if you were to take a 2-dimensional vector field and if you were to kind of attach a 0 at the end and then compute the 3-dimensional curl and then dot with your fictitious k vector, it's true, you would get exactly this formula. But that's a bunch of made-up fiction to allow you to use a notation which, let's face it, doesn't particularly give you any advantages over these also very convenient and compact notations. So I really I'm really not okay with this notation. Okay, how are we doing? Is everybody with me? Okay. All right. Now, believe it or not, we are ready to go ahead and state Green's theorem. We have all of the elements that we need to put together. Green's theorem, now you can see right here what the punchline is going to be. The punchline is going to be that a certain vector line integral and a certain double integral are always equal, which is pretty weird when you think about it. But anyway, how do we get there? And the way we get there, first idea is to recognize that circulation is a quantity of interest. So yes, we can think of this as a vector line integral. We can think of the object in question as being the vector field, but let's not. Let's think of the object in question as being the integral itself. So there's a stuff that we're interested in. It's called circulation. Keep in mind, we've made the observation that it accumulates. Right? This was one of our big points. So circulation on the whole region, the whole interior, is the sum of the little bitty circulations that you have on all the pieces that you chop it up into. Whole is the sum of the parts. This, innocent observation. This is exactly the chop it up, add it up that we did for mass and work and every other thing that we computed with double integrals. So the mere fact that it accumulates that lets you do this. And then our density statement above. Let's see if I can. Here we go. Our density statement is that a little piece of circulation is circulation density times area. And notice that's all I've got here. Little piece of circulation is circulation density times area. Right? So I'm using the idea that that is a density to rewrite d sigma as dA. How we doing? Now, I have just thrown a ton of weird and sophisticated ideas at y'all. It's a ton. I am not expecting that y'all have been 100% digesting all of this as we've been going along. It's too much, right? Give yourself the benefit of time to let this soak in. If it might be helpful to re-listen to some of the video recording that we're making right now, fingers crossed technology, then you go ahead, absolutely, right? But one way or the other, there's a lot to chew on and a lot to digest here. So give yourself time to do that. Okay, but that said, we do have a shiny new theorem that we can use, Green's theorem. And you can interpret this a couple of different ways. You can interpret this as if you have a line integral, and if that line integral is around a boundary, then check it out. I can compute that line integral instead by computing this double integral. And by the way, you can also go the other way. If you had a double integral, and now it's harder to use it the other way, but if you had a double integral and if you knew somehow that your integrand was Green's operator of a known vector field, you can see why that's weird. How would I know what this vector field is? That'd be kind of hard to sort of figure out. But hypothetically, if you did, then that double integral of that Green's operator, alternatively, you compute with a line integral. And I am actually going to show you one example of that in a couple of minutes. But first, let's do one of the sort of relatively straightforward ones. Here we go. We have a curve. Like so. It's the unit circle. Now, importantly, it's the clockwise oriented unit circle. By the way, now a lot of y'all might be thinking, hey, no fair. Isn't it supposed to be counterclockwise? Boundaries are counterclockwise. I'm not saying that this is a boundary. I'm not restricting my attention only to curves that happen to be boundaries. I hope it'll be a boundary because that's a requirement of the theorem. But this is a perfectly good curve just as a curve. Okay. So given that curve and given this vector field, I can ask what is the integral of that vector field over that curve, namely how do I compute this circulation right there. Okay. Now I've already kind of given away the big problem. The problem is that this curve, let me do it again, this curve is just not a boundary. Right? It's not. It violates the big rule. If it's going to be a boundary of that disk D, it would have to go the other way, and it isn't, so it's not, and we lose. You cannot invoke Green's theorem on this curve here. Does everybody see the problem? Okay, bummer. But here's the way we can fix it. It's not even that hard of a fix. I can just imagine, okay, well, if I were to just go the other way, right, and keep in mind, going the other way, all you got to do is just say so with sort of a minus sign exponent. If I were going the other way, that is a boundary. That's the very clearly, right? That's the boundary of this disk D here, right? So I do have a way of viewing the circle. I'm gonna worry about the boundaries, but that circle, oriented appropriately, is a boundary. So what I'm going to do is I'm going to apply Green's theorem to the dark blue curve, even though the purple curve is the one I actually want. I'm talking about this other oriented curve, the dark blue curve, and again, it's a different curve. How does that help me? The way it helps me is I know that these two curves are simply opposite orientations of each other, and I know that just means minus sign. Right? So, so the curve that we are interested in relates to the curve that actually is a boundary by way of it having the opposite orientation, which just gives me a minus sign right there. Now let's take a moment, make sure everybody's comfortable with that. Everybody see what happened? Got to be real careful about orientations. By the way, let me dispel a misunderstanding about orientation. Oh, sorry, you had a question. Yeah.
Wouldn't the integral of that region D,
What does that require you to have both C and NOx?
Both of these curves go all the way around. I didn't want the blue and the purple to sort of over. Yeah, no, they're both the entire circle. It's just that what I have in purple needs to go clockwise, and if I had gone all the way around, it'd just be confusing picture. No, you're totally right. It does have to go all the way around. Yeah. Okay. All right. Quick dispelling of myth. A lot of people will view this minus sign as being. It's just a sign. It's just, come on, we all make sign errors, right? I'm not above sign errors. I make sign errors here and there. And on an exam, a sign error is not that big of a deal. Because on an exam, it's, you're moving fast, right? It's a triviality that's just, it's a matter of counting how many minuses there are. Come on, this is not a big deal. Okay, I want to be very clear. That's not what this is. This minus sign is the result of a significant and subtle and sophisticated idea. This is not a miscounting of, I had 5 negatives and somehow I miscounted 4 and that's not what this is. This is talking about a relationship between orientations. It's talking about boundaries. It's talking about the convention of what the orientation is on a boundary, and that's a substantial thing, right? So be really, really careful with orientations, and if you need one of these minus signs, well, let's see, let me say that more generally. If you get this sign wrong, it's a problem, right? It's a significant part of the intellectual background of the problem. So take that very seriously. On a 20-point question, that minus sign right there could easily be worth 4, maybe 5 points. It's a big deal. All right. Cool. So we have our scenario pretty much dealt with at this point. We've got there's a minus sign that I'm going to have to, not lose track of. But otherwise, I've got an integral over a boundary. Integral over a boundary relates to a double integral over the interior by way of Green's theorem. Right? Green's theorem is that this line integral is equal to this double integral. Everybody with me? So we have successfully turned a question about a vector line integral into now, it's basically just a double integral. Now, okay, fine, I've got to compute this thing called Green's operator. How do I compute Green's operator? Green's operator is something that you do to a vector field. Here's our vector field. Green's operator computes according to a certain formula that, again, you all have on the previous page. Make sure to know that formula for Green's operator, dq dx minus dp dy. You've got to have that locked and loaded, ready to go. And conveniently, the x partial of the second coordinate, q, here is easy. Lucky break. And the y partial of this first component, p, here, really easy. Now, again, I crafted this question so that it would work out nicely, obviously, right? But really easy to compute Green's operator. It's just 2. Easy double integral, problem solved, answer. Everybody cool? Let's think about what the alternative would have been, hypothetically, if we hadn't used Green's theorem here. If we had just brute forced this, and all of this goes in and is my vector field. Now I've got tangent and exponentials and stuff like that, but it's worse. It's worse because on this curve, keep in mind, what are x and y on that curve? X and y on that curve have a lot of trig in them. That means that this x is trig ugliness, and this y is trig, and this y is trig, and that x is trig. So this is not just an exponential. This is an exponential with trig inside of it. All right? This is bad. We don't really want to have to do this anymore. So brute force, really hard problem. Using Green's theorem, it's a snap. Okay. All righty. You know what? I think we're bound to be out of time by now. Let's see here. Well, we have 10 seconds. We'll draw the line right there. Y'all have a good rest of your Monday. See you later.